Pre-Calculus Chapter 2, Lesson 6, and we're going to look at now graphing these rational functions. And this is a review of something we did last year, and there's 7 steps, and what I'm going to do is to cover each one of these steps very quickly, talk a little bit about how you do each step, some of the things you need to be aware of, and then we'll go on from there in the next video and actually just do a video of examples so you can kind of watch me do those 7 steps in order as we graph these rational functions. The main thing to remember is that if you need to do these steps in order to make sure that you get all of the points of the graph in place before you actually start graphing them. And these are those functions that we did last year where we look at the horizontal asymptote, we look at the vertical asymptotes, we're going to find the x-intercepts, we're going to find the y-intercepts, and then once we have all that in place, we'll use the analogy of the snake starting out on the right, and then we'll use the snake as he comes from the right and works his way to the left, where he can cross, what he has to jump, and those types of things. So hopefully you remember a lot of that stuff from last year. Again, I'll talk about each one of these steps a little bit. It should be mostly review, a couple of new things that I'll emphasize as we go through, as I said, and then we'll, in the next video, actually just do some examples. So let me cover those steps and some key points, and then we'll move on from there. The first thing that you'll want to do when you're doing these graphs is to determine what the end behavior asymptote is. Now, in a lot of cases, this is going to be a horizontal line, and from last year, I hope you remember the way to do that is to compare the degrees of the numerator and the denominator. And there's 3 scenarios, and let me open up your book and show you in your book what it says, so if you need to reference it, you can. In your book, it has this little chart and it talks about the graphs and the end behavior asymptote, and it has these 3 scenarios that we looked at last year. First, if the degree of the numerator is less than the degree of the denominator, your end behavior asymptote is going to be the line, the horizontal line, y equals 0. If the degree of the numerator and the degree of the denominator polynomials are equal, then your horizontal asymptote is the line y equals a over b. And you remember a is the leading coefficient of the numerator polynomial, and the b is the leading coefficient of the denominator polynomial. Okay? If the numerator degree is greater than the denominator degree, then the end behavior asymptote is not horizontal. There is no horizontal asymptote, as we said last year. There is an asymptote, however, and it is determined by actually doing the division problem, and it ends up being the quotient of your division problem. Now, what does all that mean? Basically, it means this. Well, let me show an example. Next page. Here's an example where the numerator degree is 3, the denominator degree is 2, which means the asymptote, or end behavior asymptote, is not horizontal. So what is it? So the way to determine that is to actually do this division problem. Now, I cannot use synthetic division because this is not a linear factor. So what I need to do is actually divide x cubed by x squared minus 9. And so we simply divide x squared into x cubed and we get x, and then we divide x cubed minus 9x, and then we add the opposite, so this is 9x. Okay? Now, x squared does not go into 9x, so 9x is my remainder. So the quotient is x. So when I divide this out, I actually get the problem, the numerator degree is equal to the denominator, so this is my answer, x, that's my quotient, plus the remainder. Now, the thing to think about this is we're talking about end behavior, so we're talking about putting in very, very large numbers for x. Now, as I put in very, very large numbers for x and square them for this denominator becomes extremely large, meaning this fraction gets closer and closer to 0, because remember, as the denominator gets bigger and bigger and bigger, that number gets smaller and smaller and smaller. So as you go out towards positive infinity, this gets closer to 0, so what you actually end up doing is having this very large number plus 0, so the end behavior simply ends up being whatever this x value is. So in essence, what happens is, as you put in large number, your end behavior actually ends up being this quotient, y equals x. So what that means is this. As you go, you graph this line, y equals x. So as you go out towards positive infinity, this graph is going to approach this line y equals x. So the graph is going to be approaching this line, never crossing it or touching it, out here at its ends, out here and out here. So the end behavior is going to be out along this line y equals x. Now when you do this division problem, it doesn't always come out to be linear. In other words, what if this was x to the fourth? Well, if you divided x squared into x to the fourth, you get x squared. So actually, in that case, your end behavior is a parabola, which means as you go out towards positive infinity this way, the graph is going to get closer and closer to this parabola as it goes up, and maybe closer and closer to the parabola that goes up here. So your end behavior can be linear or quadratic or cubic. It could be anything, and it all depends on what you get when you actually do this division problem. So if the degree of the numerator is greater than the degree of the denominator, you're going to have to do some division to find out what that end behavior actually ends up being. All right. Now, one final note about end behaviors. Let me go back to our list and I'll talk about it then. A final note about our end behavior is this, is the graph can cross this asymptote in the middle of the graph. Meaning, if it's a horizontal line out there at the ends, it will not cross or touch the asymptote out there at the ends, just like it doesn't cross or touch any other asymptote. However, in the middle of the graph, around 0, or in that towards the middle of the graph can cross that horizontal asymptote. So that's why the more accurate name is the end behavior asymptote, because it controls the end behavior and what it can do out there. It doesn't really create a place where it can't cross in the middle of the graph. So just remember that as you're doing your snakes or as you're drawing your graphs. Okay, so the first thing you want to do is to figure out your end behavior asymptote, and the way to do that is to compare the degrees of the numerator and the denominator. The second thing you'll want to do then is, once you've determined that, is to completely factor the numerator and the denominator. And you'll need to do this in order to complete the next two steps. So it's very important that at some point at the beginning of your function you completely factor the numerator and denominator as best you can, or completely. Okay? Step 3 then is we're going to determine the vertical asymptotes. So the vertical asymptotes are determined by the zeros of the denominator, which is why we needed to factor it. So any denominator, a linear factor of the denominator, will create a 0, which means that will be where the vertical asymptotes occur. Now, unlike the horizontal asymptotes, the graph can never cross your vertical asymptote. Those are permanent, impenetrable boundaries that the graph cannot cross. Now, it will show up on the other side, but it cannot cross it in any place. And the way to determine those is to any 0 of the denominator. And I'll talk about this after I talk about the next step. The fourth step is to determine where the x-intercepts are, and the x-intercepts are the zeros of the numerator. Okay, so when you're looking for where it can cross the x-axis, it can only cross the x-axis where the numerator can be made 0. And if you think about it, it makes sense, because you're talking about x-intercepts, and that's on the x-axis, and all of the y values on the x-axis are 0. So the only way this is an x-intercept is if the y value is 0. So if you cannot create a 0 in the numerator, thus creating the entire polynomial being 0, you'll never make that whole fraction 0. So the zeros of the numerator will be the only place where it can cross the x-axis. Now you'll notice that in both steps 3 and 4 I say not in common with the numerator or not in common with the denominator, because what happens when you have common factors or common zeros is that creates a whole, not an asymptote. And it also creates a whole, not an intercept. So if you have a 0 that's the same in both the numerator and the denominator, in other words, if I have the quantity x minus 1 in the numerator and the quantity x minus 1 in the denominator, that's going to create a whole in my graph, neither a vertical asymptote nor an x-intercept. Okay? Next step. After you've done that, then you'll want to figure out where will this cross the y-axis. And the y-axis is what you get Where it crosses the y-axis is what you get when you substitute 0 into the expression. Again, on the y-axis, the x value is 0, so we're going to substitute 0 in for every x, and that will give me the y-intercept, or where it's going to cross the y-axis. Now, just so you know, for our purposes, it can only cross in one place. You can only cross the y-axis in one place, so you want to determine that by substituting in the value 0. Once you've got all of these parameters in place, you've kind of given the framing for the graph, you can then begin to sketch the graph. You'll want to start in positive infinity, and you want to figure out if you start above or below the graph. Now, if the intercept or the end behavior asymptote is y equals 0, you'll just want to answer this question. Way out there in positive infinity, is the entire function that I'm looking at, as I'm putting in very big positive numbers, is the entire fraction going to be positive or negative? So basically you can look at each linear factor, figure out if it's going to be positive or negative, multiply them all together, and if it's positive, it's going to start above the 0. And so then you'll start above, and then you'll go from right to left and connect all of the points without crossing any vertical asymptote. If it ends up being negative, then you'll start below. Now the question comes, what happens if that horizontal asymptote has been shifted up to, let's say, positive 3? Do you start above positive 3 or below positive 3? And a lot of times that can be determined by where the x-intercepts take place. If you're above the x-axis, or above the end behavior asymptote, and you have an x-intercept below that, well, how are you going to get there before you run into the vertical asymptote? The only way to do that is to start out below the asymptote, so you can go down and go through that x-intercept. So sometimes it's just an exercise in logic about figuring out where I should be above or below, and that's going to be the best we can do, at least as much as we want to talk about it here. I'll do a few examples and hopefully that will be more clear. Once you figure out where you're going to start out there in positive infinity, you simply draw a line as if you're a snake, remembering that you can never cross a vertical asymptote, and you can only cross the axes at the intercepts, and then you just connect all those points and you'll have your graph. So that summarizes the steps, a few key points. In the next video I'll do a number of examples, or in class I'll do a number of examples. You can follow those steps, and then hopefully you can do those graphs on your own from there.